All right, let's jump right in. We all want our critical stuff, like the power grid, to be as safe and secure as possible. And common sense would tell you that more defenses is always better, right? Just pile it on. Well, here's the twist. In the world of cybersecurity, sometimes adding more defenses can actually make you weaker. So, to get our heads around why that is, we've got to look at what we're actually defending. This right here is a model of a modern smart grid. And believe me, it's not just poles and wires anymore. It's this huge, interconnected web of sensors, communication hubs, control nodes, all the stuff that keeps our lights on. It's a perfect example of what engineers call a cyber-physical system.
And what exactly is a cyber-physical system, or a CPS? Well, to put it simply, it's where the digital world smashes right into the physical world. It's the invisible brain making real-world things happen, managing power flow, running our factories, even coordinating medical devices. This stuff is, quite literally, the backbone of our modern world.
Which brings us to a really critical question. This invisible system that keeps everything running, it's also an invisible battlefield. So what happens when an enemy decides to attack it? Look, to defend any system, you first have to understand how an attacker thinks. And researchers have pretty much boiled it down to three main ways a sophisticated attacker can make something like the power grid fail. So let's take a look at the enemy's playbook. First up is what's called attrition failure. The best way to think about this is like a long, drawn-out siege on a castle. The attacker isn't going for one big knockout punch. Nope. Instead, they're just patiently taking out your components, your digital soldiers, if you will, one by one, until the system is so worn down it just stops working. Next, we have pervasion failure. And this is way more insidious. This is like having spies inside your fortress walls. The attacker doesn't destroy your components, they compromise them. They turn your own digital soldiers into traitors that work together to cause chaos and overwhelm the good guys from the inside. And finally, there's exfiltration failure. With this one, the attacker is like a thief in the night. Their goal isn't destruction, it's information. They want to steal your system's secrets, its battle plans, so they can either get an intelligence win or, worse, set the stage for a much, much bigger attack later on. Now, this table here really connects all the dots for us. You can see how a quiet, surveilling attacker, represented by the little eye icon, is aiming for that exfiltration failure. But in contrast, a destructive attacker, shown as the bomb, is going for the brute force of attrition, or the chaos of pervasion. Different goals, totally different methods. So, now that we kind of get the enemy's playbook, how do we actually fight back? Let's open up the Defender's Toolkit and see how we're supposed to build a stronger fortress. We really have three main strategies here. First, there's redundancy, which is basically just having more components than you absolutely need. Think of it as having extra soldiers in the barracks, just in case. Second, intrusion detection systems, or IDS. These are your guards on the wall, always looking for trouble. And third, data leak rate control. That's like having guards at the gates, making sure no secrets get smuggled out. So at this point, the solution seems pretty obvious, doesn't it? Just max everything out. More soldiers, more guards, stronger gates. Just build the biggest, baddest fortress you possibly can. Simple, right? Well, this is where it gets really fascinating. Because the research shows that what seems like the most obvious solution can actually blow up in your face. Welcome to the security paradox. So, here it is, the crucial point of all this. In the super complex world of cyber-physical systems, more is not always better. The very defenses you build to protect yourself can, under the right conditions, create brand new vulnerabilities. And this right here, this is where the research gets wild, because these graphs show you that trade-off in action. So first, let's look at the attrition graph on the left. That bottom line, alpha. That's just adding more redundant nodes, more soldiers. The line going up, MTFTF. That's how long the system survives. See how that line shoots way, way up? More redundancy makes the system way stronger against a siege. Okay, but now look at the exfiltration graph on the right. Using the exact same increase in redundancy, that same alpha value, look what happens to the system's lifetime. It tanks, it plummets. Why? Because more soldiers gives the enemy more potential spies to recruit, which actually makes you weaker. So why on earth does this happen? Well, it really comes down to two big trade-offs. First is the redundancy paradox. Having more soldiers means an attacker has more potential targets to turn into spies. More nodes means more ways for data to get stolen. And second, you've got the guards dilemma. If your intrusion detection system, your guards, are too jumpy, they start making mistakes. They see threats that aren't even there and end up kicking out your own loyal soldiers by accident. That's called a false positive, and it literally weakens your own army from the inside. So all this means the goal can't be just maximum security. The real goal is resilience. And to get there, we have to find that security sweet spot. You see, true security isn't some kind of arms race. It is not about brute force. It's this delicate balancing act. It's all about finding that perfect, optimal point where your defenses are strong enough to stop the bad guys, but not so aggressive that they start hurting you instead. And this graph right here is the proof for our guard's dilemma. It shows the overall system lifetime against all kinds of attacks. So on the bottom, you've got the detection interval. That's how often your guards are checking the walls. If the interval is too long, that's over on the right, you're not checking often enough, and the system's lifetime is pretty low. But as you check more frequently, moving left, the lifetime goes up, but only to a certain point. It hits this peak. Then, if you check too often, the lifetime starts to drop again. That's your overeager guards creating too many false positives. The best performance isn't checking constantly, it's finding this perfect sweet spot right there in the middle. As the researchers themselves put it, redundancy should be used with caution, because while it suppresses attrition and pervasion failure, it also induces exfiltration failure. I mean, that's a perfect summary of this whole security paradox. And all of this leaves us with a really vital question for our future. As everything around us gets smarter, our homes, our cars, our cities, they all become these complex cyber-physical systems. So how do we design their defenses intelligently, making sure we're not accidentally building the very weaknesses that could one day bring them all down?